Welcome back. Today, guys, we're going to talk about gases. Why? Because they're important. Think about what our life would be like without gases. In fact, we wouldn't have a life without gases. What's the most important gas to us? Oxygen. We need it to survive, right? We can go a month, 6 weeks without food, 7 days maybe if we're lucky without water, but if we don't have oxygen within 4 minutes, we cease to exist. So today we're going to talk about gases and the property of gases and how those kind of affect our body. So hang with me on this. First thing we need to talk about, if we're going to talk about the properties of gases, is what we call the kinetic-molecular theory. And the kinetic-molecular theory explains the physical properties of gases. It describes the behavior of the particles that make up a gas. And it's based on what we call a postulate. A postulate is just a series of scientific statements that are assumed to be true unless we prove otherwise. Why do we use them? Well, they support the theories, kind of like the kinetic-molecular theory that we're going to talk about here. So let's go ahead and look at the different postulates that make up this theory. The first one is that a gas consists of very small particles, each of which have a mass. Think about gases we know. Oxygen, right? Well, we know oxygen has a mass. It has an AMU value of about 16, right? Or 16 grams per mole. So it does have mass. Okay. The second part says that the distance separating the gas particles are relatively large. Think back when we talked about phase change, right? Particles of a gas, or a solid, are really close together. We add a little more energy, they start moving apart, breaking those intermolecular bonds. We add more, they move far apart and turn into a gas. So the distance separating them is relatively large. This allows us to compress gases. We can push those molecules back in together. There's a lot of space to them. We can condense that space. Because of so much space between them, what we see is that gas has a relatively low density. Remember, density is mass per volume. They have a really light mass and they have a huge volume. So as we condense them, what we see, our density does increase, but it's still relatively low. The third part of the kinetic molecular theory says that the gas particles are in constant, rapid, random motion. Remember, to get to the gas phase, we have to add a lot of energy. So they are constantly moving around. And because of the fact that they're constantly moving around, this allows them to take the shape of the container they're in. Think about if you blow up a beach toy, right? Some little crab floaty or something like that. It's going to take the shape of that container, that blow-up towel. Or a beach ball, it's going to take that round shape. So because they're constant motion, it'll take the shape of the container. The other thing that we see is that when we look at the collisions between different gas particles and the walls of the container, they're going to be what we call perfectly elastic. What this means is that when these particles collide in each other, they do not lose energy. Remember, energy is never created or destroyed, right? It only changes form. Well, with gas particles, we say when they bounce into each other, they're actually not, that energy is not changing form. It's retaining, those particles are retaining that energy. They're totally elastic. Think about if you had like a super ball that you could throw and it kept bouncing forever. That would be a perfect elastic collision. Okay? This perfect elastic collision means that the gas particles are not going to slow down, therefore they're going to take the shape of their container. Okay? And as they run into the walls of the container, they're going to create a pressure. Okay, think about trying to blow up a balloon. Well, the only way you can blow up a balloon is when you put air in it. You got to create enough pressure inside that's pushing those edges of the balloon out. Well, how come you're doing that? You're putting more air particles in there and it creates a pressure. Okay, so pressure is simply caused by the impact of gas and the container. It's creating this outward force. The particles are pushing out on it. Okay, and we measure that outward force as pressure, which is force per unit area. We'll talk about in a little bit here different ways in which we actually measure the pressure of an area, but just understand that for now, that pressure is the force that particles exert on their container. Next postulate says that the average kinetic energy of gas particles depends only upon the temperature of the gas. Let's go back to phase change, right? As we added more heat, we add up more energy to the system. Well, the same applies to gas particles, right? If we increase the temperature, we're going to increase that kinetic energy. Remember, kinetic energy is the energy of movement. So more temperature, we get more movement. Okay. Also, we assume that the gas particles exert no force on each other. And what we mean by that is that any attractive force that may exist between different particles is so small and so weak that for our purposes we just ignore it. We say it's non-existent. Okay. Now earlier we talked about pressure. Remember, pressure we said was created by the particles running into the edge of the containers. Okay, it's an outward force created by these particles spread over a given amount of area. Okay, it results from the collision with the gas particles with each other and also the container, the object that they are with. So if we increase the number of molecules inside a container, we're going to increase the number that hit the surface, and then we increase the pressure. Think about each time you blow into a balloon. You're putting more particles in, your balloon's expanding. Well, in order for that balloon to expand, you have to increase the pressure. Pressure has to get greater on the inside than it is on the outside, so it expands out. The other thing that we can see is that if we increase the temperature, we're given that more kinetic energy. Well, if more kinetic energy means that particles are going to collide with that container more often. If they're colliding with that container more often, we're going to get an increased pressure on the inside. The opposite is also true, that if we decrease the temperature, the molecules are going to have less energy and they collide less often and decrease. This reminds me of my son's birthday party this year. We went to the store. His birthday's in March. It was a cold day. We bought him some of those Mylar balloons from the grocery store. They're nice, blowed up. As soon as we took them outside, all of a sudden they started shrinking. Why? Well, cold slowed down the molecules, gave it less kinetic energy, less pressure. Then we went inside again, it heated them up, and the balloons blew back up. So that's an example of how the temperature can increase it. Another example is if you take a bike tire and you take it up over, you leave it out in your car, let's say, and the heat pounds down all day. Well, you may end up blowing your inner tube because it's putting so much more energy into there that it's increasing. Maybe the pressure is going to be too big for that inner tube and it pops. Now, measuring gases, we already talked a little bit about this earlier in the year. Okay, but the amount of gas, remember, amount of anything we measure in a mole. And if you remember what we talked about earlier when we did our conversions, that 1 mole of any gas occupies 22.4 liters, as long as they're at the same temperature and pressure. Well, when we measure gas, we're talking about the volume of it. And remember, gases fill their container. Okay, so the volume of a gas is going to be whatever the volume of that container is. Okay, so that's an easy way for us to figure something out. If we have a 2-liter pop bottle, empty it and just put atmosphere in there, gas, we have 2 liters of our gas. Couple reminders, remember that 1 liter is equal to 1,000 centimeters cubed. This is going to be important for doing conversions. Okay. Now, when we talking about gases, we are going to measure the temperature, talk about the temperature in terms of Kelvin. Okay. If you remember, Kelvin is equal to whatever degrees Celsius is plus 273. The reason we do this, because later on we're going to get into some calculation. And if we get into negative numbers, the calculations don't work correctly. So we use Kelvin because remember, the lowest temperature Kelvin is 0 degrees Kelvin. So we never get into that negative range. Last thing we'll talk about in measuring gases is when we talk about measuring pressure. There's a bunch of different units we can use to measure pressure. But when we talk in terms of science, the SI, or the accepted unit, is what we call the pascals. And I'll relate this back to atmosphere. Remember we talked about atmosphere when we talked about diving, okay, and scuba diving and stuff like that. Well, 1 atmosphere, which is generally our atmosphere at the surface of a body of water, or at the ocean level, is equal to 101,325 pascals. Or we can also express that in kilopascals, which would be 101.32 kilopascals. So that's the SI unit. A couple of things you may be more familiar with, and that is millimeters of mercury. A lot of times when you're watching the news, they'll talk about the barometric pressure in millimeters of mercury. 1 atmosphere is equal to 760 millimeters of mercury, or what we call 760 millimeters torrs. The torrs and the millimeters of mercury are the exact same unit. If I'm not mistaken, that torr is the guy who figured it out, so they named the unit in honor of him. One more that you're probably even more familiar with is the idea of pounds per square inch. Let's say you go to blow up your bike tire. If you got a mountain bike tire, you're probably putting anywhere between 32 to 40 pounds per square inch. Or if you're doing a road bike tire, it's about 100 to 120 pounds per square inch. Well, 1 atmosphere is equal to 14.7 pounds per square inch. Now, I'm not going to expect you to memorize these. I will give those to you on a test. What I do expect is that you're able to use factor labeling to convert between those. Okay, so you're able to set up those ratios. So make sure that you can do this. But I will give you the units for the pascals, the kilopascals, the atmospheres, all those on the test. You don't have to memorize them. You just have to be able to convert between them. Now, when we talk about gases and compare gases, we have to do it at what we call STP, which stands for standard temperature and pressure. Remember when we talked about 1 mole is equal to 22.4 liters for any gas, as long as they're at STP? Well, if we're going to compare gases, because they're affected by temperature and pressure, we have to standardize our temperature and pressure we talked about. Okay, so our standard temperature is 273 Kelvin. What's that going to be in Celsius? 0 degrees Celsius, right? Our pressure then is 1 atmosphere, which is equal to 760 millimeters of mercury, or 101.325 pascals, or 101.33 kilopascals. These are what, when we're talking about standard temperature pressures, these are what we're holding them under. Now, where's this 1 atmosphere come from? Well, 760 millimeters. Basically, what we see with the 760 millimeters, it's the amount of pressure required to support a column of mercury 760 milliliters at 25 degrees Celsius. So let me show you what I mean by this. So here's an open container. We put like a test tube in here. And as air pressure pushes down, it pushes the mercury up in there, and we can actually measure it. At 1 atmosphere, what we see is if we measure this, it's going to be 760 millimeters, 76 centimeters. And so that we say is 1 atmosphere. That's where we get the standardization of that value for. Just a little background information for you. So let's talk about some practical application of this. As far as atmospheric pressure, remember, atmospheric pressure is just the amount of weight that's of the atmosphere pushing down you. Remember, the atmosphere is made up of particles, right? Oxygen, nitrogen, carbon, a bunch of other stuff in there, but in smaller amounts. And it has weight. All those have formula weights or atomic weights, and they're pushing down us. Gravity's pulling them down. So what we see is that the amount of pressure is going to vary with altitude, okay, and the amount of gases pushing down. If you increase your altitude, get up higher, you're going to decrease your pressure because you have less particles pushing down on you. Let's say if you're on top of Long's Peak as compared to if you're standing on the ocean. You're just higher up, so there's less particles. The other thing that we see atmospheric pressure varying with is that's the composition of the atmosphere. Now, granted, our atmosphere that we breathe is about 78% oxygen, 78% nitrogen, 22% oxygen. But what also varies is the amount of water. You got to figure that water is going to weigh more than either nitrogen or oxygen. So the more water in there, the higher our atmospheric pressure is going to be. So that can affect it as well. And how do we measure the atmospheric pressure? Well, that's with a barometer. So if you're watching, like I said earlier, if you're watching the weather, let's say the barometric pressure is 760 millimeters of mercury. So this is what we use to measure pressure with. And as I said, it's in millimeters of mercury. So let's say we're standing right here at the ocean. Let's just look up at a column of air above it. So at the ocean, we have all these particles pushing down. They're all weighing on us. Now let's say we go up to Mount Everest. We magically appear up there. If we magically appeared on top of Everest, we'd probably live for about 3 to 4 minutes before we die of oxygen deprivation. That's why when people go to climb it, it takes them so long. They have to acclimatize for it. But up here at the top of Mount Everest, with just almost 9,000 meters, look, there's very few total particles up there as compared to down here. So the atmospheric pressure is less. Higher we go, then lower. Okay, so as we decrease this atmospheric pressure, 2 things happen. First of all, the oxygen molecules become more dispersed. They become farther apart. So when we're on top of Mount Everest, each breath we take in, if we could breathe up there, which people can without oxygen, you're getting less particles in than you do at sea level. Okay, so at higher, we breathe less oxygen at higher elevations. Well, why is that a problem? What do we need oxygen for? cellular respiration, making energy. Okay, so it's harder for our cells to make energy the higher we are because there's less oxygen available. One way we can measure this is what we call O2 saturation. If you've ever gone into a hospital, one thing they do is they put a little probe on your finger and measure your O2 levels. Generally, most healthy people at sea level, they're about 98% oxygen saturated. If you go up to 6,000 meters, okay, a little higher than we can get here in Colorado, but your oxygen saturation drops down to 67%. Imagine you go up another 2,000 meters, okay, to 8,000, or another 3, almost to 9,000 meters. Imagine what the saturation level of those people that are climbing Everest without oxygen. Very, very low. So that's why it's so hard to perform up at higher levels. Okay. The other thing is that we see going on at higher elevations is there's less pressure to affect you and the gases inside your body. So like we said earlier, it's harder to get the oxygen to tissues and cells. So you're not able to perform cellular respiration. You're not as efficient. You're not able to burn your food. That causes problems. Okay. The other thing we see that can affect atmospheric pressure is the weather and the latitude. Okay. If we get a low pressure front coming in, low pressure means it decreases the pressure over an area. It can actually make you feel 500 to maybe 700 feet higher in elevation than what you actually are. Here in Colorado, it's not a big deal. We're used to going up and down that all the time. But imagine you live in Florida. That may mess with your body a little bit. Okay, all of a sudden being 500, 700 feet higher, so to speak. The other thing we see is that atmospheric pressure will vary where your latitude is. Latitude, remember, is the degrees north and south equator. Okay, pressure is greater at the equator than it is at the poles due to the odd shape of the Earth. Okay, what this means is that if we're standing at a 12,000 foot peak in Alaska, it's going to seem much higher than that same 12,000 feet peak in Mexico because there's more air pushing down us in Mexico than there is in Alaska, so there's more pressure there. Just a couple of interesting things. Now, how does this relate to us? What is something that we see here in Colorado? And one of those big things is altitude sickness. Now, if you live in Colorado, you probably don't experience this too much unless you go climbing a bunch of 14s. But think about, you have relatives coming in from maybe the East Coast, West Coast, where they're at sea level. Okay, they may experience what we call either altitude sickness or mountain sickness. You can leave here in Loveland and take them up to Estes Park to go hiking for the day. Okay. Estes Park is about 8,000 feet, just over 8,000 feet, and they start seeming a little sick. You know, symptoms include things such as headaches. They start feeling a little achy. They have a lack of energy. They don't want to walk around. They just want to sit in the car. They lose their appetite. They start feeling nauseous, a little queasy. They get dizzy. Okay, they start vomiting. Maybe they have shortness of breath. These are all symptoms of mountain sickness. The interesting thing about mountain sickness is a lot of times it's not related to your athletic ability. I've seen people that are bike racers come up from lower elevation and they can't handle the elevation. They get really sick. I've also seen people that are very out of weight come up and be perfectly fine with it. So it's more of an individual basis. It doesn't have to do with how good or shape you're in. And what we really worry about with these symptoms is that they're symptoms of more severe sicknesses, including what we call HAPE and HACE. HAPE stands for high altitude pulmonary edema. Edema means a swelling, taking on fluids. Pulmonary refers to your lungs. Okay, so you're getting a swelling or a buildup of fluid in your lungs, very bad. Even more concern is what we call HACE, high altitude cerebral edema. Cerebral is your brain. So you get a buildup of fluids in your brain. Both of these can be life-threatening. When people go climb mountains, if they ascend too quickly when they're doing these big peaks like Everest and K2 and even Denali, they can get these symptoms. And only really cure for this is to get them down quickly get them to lower elevation so their body can recover. So today we talked about the kinetic molecular theory, which describes the property of gases. The physical properties also. We also then talked about ways that we measure gases, talked about how we measure pressure, we talked about temperature, standard temperature and pressure. We also talked about how different units of pressure and how to convert between them. Remember, you won't have to know those values. I'll give them to you in a test, but you will need to convert them. And then we talked about practical applications of pressure as it relates to our atmosphere. Here live in Colorado, symptoms of mountain sickness, altitude sickness. Okay, so if you have any questions, please come see me before class and we'll get them taken care of. Until next time, guys, take care. I'll talk to you later.